Hello everyone, welcome. This is an educational channel where we go over usually people who have come up with a theory of everything about something that I think is worth noting, worth paying attention to, and so we cover it here. And today is the 200th video that we've done on the reciprocal system of theory, which is an important theory that was derived by Dewey B. Larson back in the 20th century. He died back in 1990, but before he did, he put out maybe a dozen books, 15 maybe, and many articles, and gave a lot of talks on his reciprocal system. It is a system of theory, which means that if you understand how the reciprocal system works, then you can use it yourself to apply it to other subjects, any subject. And Larson applied it to many subjects. In particular, we're looking at his book right now called Nothing But Motion, which is on mostly atomic physics. There's a little bit of organic chemistry at the end. And the basic idea behind the reciprocal system is that this universe that we live in is a universe of motion. Not a universe of matter, not a universe of energy, but a universe of motion. Motion, in Larson's formulation, is a relationship between space and time. That relationship is basically, it's a ratio or a fraction. And time and space are the two components. A relationship between space and time. So if you have a fraction, time or space is the numerator, and space or time is the denominator. But it is a bit more complicated because space and time both have their coordinate aspects, which means that they both come in 3 or more dimensions, XYZ coordinates. We generally recognize that for space, that it has 3 or more dimensions. And time also has 3 or more dimensions, or at least an aspect of it does. Time and space are identical to one another, except that they are reciprocals of one another. So they have all the same qualities, but they are inverses of one another. They also both have their clock aspects. We recognize this in time. The clock of time is always getting later and later and later. This is a motion that has no specific direction, but it has a magnitude. And so too with time, with space. Space also has its clock aspect. Everything in clock space is always getting later and is always moving farther and farther and farther apart. We've actually observed that through the Hubble telescope, that all of the distant galaxies are moving away from each other, but in no particular direction. That is a scalar outward motion. The best way to envision this kind of motion, or at least a way to envision this kind of motion, is to take a balloon, put a bunch of dots on it with a magic marker, and if you blow up the balloon, all of the dots are moving away from each other. If you suck in the balloon, all of the dots are moving toward each other. And then space and time both also have their discrete units, meaning that they are not continuous. They come in chunks, in very small chunks, but chunks nonetheless. And if you have one chunk of space in one chunk of time, one unit of space and one unit of time, you have what Larson calls unit speed, which is the speed of light. So the speed of light is unit speed, that's 1. And so that is, in Larson's system, is the midpoint of the universe. Half of the universe is actually moving faster than the speed of light, and then half of the universe is moving slower than the speed of light. The half that's moving slower is the half that we're accustomed to, that Larson calls the material sector. And this is what brought Einstein to say that the speed of light is the maximum speed of the universe, because he was only aware of this half called the material sector. If he would have been aware of the half the half of the universe that is called the cosmic sector, the half that's moving faster than the speed of light, where the speed of light is actually the minimum speed of the universe. So now the legacy scientists don't know anything about this cosmic sector, but since there is a generalized reciprocal relationship between space and time, all we have to do is extrapolate from the material sector. Everything that happens in the material sector is also happening in the cosmic sector, except that the roles of space and time are reversed. For example, in the material sector, you have coordinate space, three-dimensional space, and clock time. The clock is always getting later and later and later. In the cosmic sector, you have coordinate time, three-dimensional time, and clock space. Space is always getting farther and farther apart. Okay, so that's an example of how the cosmic sector is identical to the material sector, except for the reversal of space and time. Now, today we are about to start chapter 15 of the chapter 15 of the book Nothing But Motion, which was written in 1979 or published in 1979. And this chapter is called Cosmic Ray Decay. So this is a cosmic ray, as we saw in the last chapter, is basically a cosmic atom. So this is the reciprocal, or the inverse, of a material atom. And we learned earlier in like chapter 10 of this book that atoms are combinations of motions. For an atom, a material atom, Larson uses a three-number way of, I'm blanking on the word. It's three numbers to notate, a three-number notation of each one of the atoms. So for example, the first number is a two-dimensional primary rotation, and the second number is a two-dimensional secondary notation, and the third number is a one-dimensional rotation. So in Larson's system, there's really four kinds of motion. There's a translational motion, there's a vibrational motion, there is a rotational motion, and there is a rotational vibration. And these can come in multiple dimensions. Everything is really like a combination of motions. So there really are no, there are such a thing as what he calls subatomic particles, but they are not really like separate things. They're all one thing. So he compares an atom to a curveball, where a curveball has a motion that's moving forward, but it also has a spinning motion. So it's got those two different motions connected with it, but it is ultimately one thing. So Larson actually, the title of his first book was The Case Against the Nuclear Atom. So he's saying, the atom is not composed of a bunch of protons and neutrons inside an atom and a bunch of electrons rotating around the atom. It's one thing, and it has these various components to it, but it's one thing. And so with say oxygen is two primary two-dimensional rotations, that's A, then two secondary two-dimensional rotations, that's B, and two negative one-dimensional electric rotations. That is C. So every atom has an A, B, C notation to it. And so in cosmic, if you're talking about cosmic atoms, you're going to end up notating them the same way. And so let's let Larson talk here about cosmic ray. Now this chapter is called Cosmic Ray Decay. So the decay is the part of that. The cosmic ray is that cosmic atom. The decay part is when a cosmic atom moves into the material sector, which is generally as a result of a powerful explosion of a cosmic star or galaxy that makes it cross over the speed of light barrier or boundary between the two sectors and move into the material sector. But in the material sector, cosmic atoms are unstable. In the same way as if something moved from the material sector to the cosmic sector, it would be unstable. And so it immediately starts to decay, go through a decay process where it decays from one atom to another, to another, to another, until it strips away all of the unstable parts of it to get to what is stable. So that's what he's talking about in this chapter, Cosmic Ray Decay. On the basis of the information developed in Chapter 14, we may describe the cosmic rays in general terms as cosmic atoms and particles which enter the material environment at the speed of light, at random spatial locations, and with random directions. Now, the reason why this is a random thing is because the connection between space and time, or the material and cosmic sectors, is scalar, meaning it has no direction, has no particular direction. And what he says is, the directions in time are not directions in space. And so there is no, so when a cosmic atom comes into the material sector, we perceive it as coming from all directions, or what he calls isotropic. No, he doesn't call it. Well, the word isotropic can be used. He calls it non-local. And so it comes into the material sector. We see it as really coming in from everywhere. So these cosmic atoms and particles enter the material environment at the speed of light, at random spatial locations, and with random directions. Here, then, are the contents of the cosmic sector of the universe as they appear very fleetingly to our observation in the material sector. Because we make our observations from the material sector. We see space, but we do not see time. We will now examine what happens to these objects after they arrive. In the earliest observed stages, the cosmic particles are known as the primary cosmic rays. As many observers have pointed out, there is no assurance that these are the original rays, as the decay process may have already begun before the primary rays are observed. The theoretical development indicates that this is indeed true, as the primaries contain a considerable percentage of particles that are clearly decay products rather than normal constituents of the original rays. In the subsequent discussion, we will follow the general practice and will refer to the observed incoming particles as the primary rays, but it should be understood that this does not imply that the observed primaries are identical with the particles that originally crossed the boundary into the material sector. Since the cosmic rays enter the material sector from a region in which the prevailing speeds are greater than unity, these particles make their entry at the speed of light. It is the decrease from a speed greater than unity to a speed less than unity which constitutes entry into the material sector. but the dividing line between the cosmic sector and the material sector is unit speed in all three scalar dimensions. The speed of the primaries therefore remains at or near unity in the observable dimension, even after the speed in total has decreased to some extent. This accounts for the previously noted fact that the observed speeds of the incoming particles are mainly close to the speed of light. Inasmuch as these speeds and the corresponding kinetic energies are greatly in excess of the normal speeds and energies of the material sector, transfer of the excess kinetic energy to the environment begins immediately on entry. Gravitational and electromagnetic forces, to which the cosmic atom is subject as soon as it crosses the boundary, accomplish part of the energy reduction. Contact with material particles is also an important factor, and a further loss occurs in connection with the reduction of the internal energy that must also take place. The cosmic atoms of maximum energy content are those of the most abundant cosmic elements, C hydrogen or cosmic hydrogen and C helium. The principal constituents of the cosmic rays, the cosmic elements of low atomic number, are therefore not only entering the material frame of reference at speeds which are far too high to be compatible with the material environment, but are also entering in the form of structures whose internal energy or rotational displacement content is also much too great. These elements must lose rotational energy as well as kinetic energy before they can assume forms that will merge with the material phenomena. The required loss of rotational energy from the atomic structures is accomplished by ejection of particles of an appropriate nature. A readjustment of some kind in the atomic motions is required at very short intervals, and the probability principles ensure that the direction of the rearrangements is toward greater stability. In the material environment, this means a reduction of the excess rotational energy. Okay, so now what he's saying, at least in part, is that when the cosmic elements explode, or when the cosmic star or galaxy explodes and sends particles across the boundary into the material sector, what we generally, it's cosmic hydrogen and cosmic helium, the lowest, the most abundant cosmic elements is what he says, the most abundant cosmic elements. These are the lowest elements on the periodic table, at least on the material periodic table. So I think that is the inverse of what was going on in the material sector, but I don't know that. So let's just keep going on. At the present stage of the theoretical development, it appears that the limitation of the lifetimes of the cosmic elements to extremely short intervals is due to the fact that the rotation in the cosmic structure takes place at a speed greater than unity, or greater than the speed of light. And this structure therefore moves inward in time rather than in space. Consequently, it can exist in a stationary spatial frame of reference for only 1 unit of time. Okay, it can exist in a stationary spatial frame of reference for only 1 unit of time. If it is moving translationally at a speed above unity in all scalar dimensions, as is true of most of the cosmic atoms encountered by chance in our passage through time, it moves away from the line of the time progression of the material sector and disappears. But this option is not available to cosmic atoms that have dropped below unit speed, and instead they separate into 2 or more particles, each of which then has its own appropriate lifetime. The natural unit of time in application to macroscopic physical phenomena was evaluated in Chapter 13 as 1.52 times 10 to the minus 16 seconds. Some of the observed particles have lifetimes in this neighborhood, but others range all the way from about 10 to the minus 16 seconds to about 10 to the minus 24 seconds. As will be brought out later, the magnitude of the deviation from unit time has been correlated with the dimensions of the spatial motion of the particles, but the exact nature of the modifying factor has not yet been identified, and for the present, we will treat it as a modifier of the unit of time, similar to the interregional ratio that modifies the unit of space in application to the time region. The limiting lifetime to which the foregoing comments apply is the limit at zero speed. At higher speeds, the lifetime as measured by a conventional clock increases in accordance with the relations expressed in the Lorentz equations, which, as noted earlier, are equally as applicable in the reciprocal system of theory as in conventional physics. The explanation of this longer life that we deduce from theory is that the particle can remain intact in the spatial reference system as long as it remains in the same unit of time. But an object moving at the speed of light remains in the same unit of time permanently, and such an object can exist indefinitely in any system of reference. The decrease in life at the lower speeds follows the mathematical pattern derived by Lorentz. From the foregoing, it is evident that the primary cosmic rays moving at the speed of light did not necessarily enter the material sector in our immediate vicinity. The rays that we observe may have entered it anywhere in interstellar or even intergalactic space. Okay, we're going to stop there. We will take over again tomorrow. I know this is difficult. Keep pushing through. Listen to me over and over, and it might sink in. But if it doesn't, just keep persevering. Thanks for tuning in. Have a great day.